We'll start by doing a bit of counting. And the reason for that is because it's very handy for computing simple probabilities. And just working backwards from why we're doing counting, an obvious, really fundamental question is, what do we even mean by probability? If you look up the Oxford English Dictionary, it will say that it's the probability, it's the likelihood of something happening. But that's just a circular definition, right? Because likelihood and probability are essentially the same thing in English. So it doesn't help us at all. But we're going to talk more about, over the course of the module, about what we mean by probability and different ways of thinking about it. But to keep you right, here's one interpretation of probability is the frequency interpretation of probability. It's relatively straightforward, and so it will keep you right. You know, if you have to get some intuition about what's going on, the frequency interpretation will keep you right, although it's not the only interpretation. So here's the idea of the frequency interpretation of probability. So suppose we have an experiment that we can repeat, I say here several times in the slide, but actually you should be able to repeat it an infinite number of times. Right? So that's a big ask. There's not many things we can repeat an infinite number of times, but suppose it's something like a coin toss or rolling a dice or those kind of things. Games of chance are constructed actually so that they can be repeated. The same game can be repeated many times. So that's the first thing. Suppose we can repeat something many times. And suppose there's an outcome we're interested in. Suppose we roll the dice and we're interested in whether a 2 or a 3 comes up. That's the outcome we're interested in. So we roll the dice lots of times and we count the fraction of times a 2 or a 3 comes up. That fraction is the probability. That's the definition of probability. If you stay inside the frequency interpretation of probability, that is the definition of probability. If we have an experiment we can repeat many times, the fraction of times the event we're interested in comes up is the probability. But you know, you can immediately see there's a bunch of problems with that. One is, what if you can't repeat an experiment many times? And actually there's very few experiments that can be repeated many times. It's quite an artificial setup. So for example, suppose you're interested in making a prediction about an election, you know, what's the probability of different parties winning. The elections only run once. So what do probabilities mean in that case? Or the stock market, where it's continually changing, you know, new information comes in, dynamics change, the external environment changes. So you can never like wind back the clock and do a controlled experiment again and again. The weather's another one, you know, the universe evolves. It's never quite the same from day to day. Okay, it doesn't change too much, but it does change. You know, we've climate change happening over a period of years. So it's very hard actually to come up with clean experiments, and so that's a big problem with the frequency interpretation. But still, if we keep that in our mind, but put it to one side, then the frequency interpretation is fairly straightforward, and the intuition it gives you will keep you right. So it's worth bearing in mind these other caveats. It's worth keeping it in mind. And what you'll see actually in the rest of the module is we're going to, because of these difficulties with how to actually even define probability, we'll sidestep them and do an approach via axioms and then build everything up. And that will allow us to include all the different definitions of probability, and we'll discuss that more. The reason to be introducing probability, if you remember, was why we're having this philosophical discussion of probabilities, because we're interested in counting. It leads us to be interested in counting, rather. And the reason is as follows. Suppose we want to actually calculate a probability. Here's one way to go about it in a simple setting. We can list all the possible outcomes of an experiment. Suppose it's throwing a dice. We've got six possible outcomes, numbers 1 to 6. If we assume they're all equally likely, and that's an assumption, then the fraction that contains the event, the number of fraction of outcomes that contains the event, for example, a 2 or a 3 would be 2 over 6 is the fraction that contains that, is our probability. And so that makes us interested in counting the number of outcomes of an experiment. But the thing is, enumerating all possible outcomes quickly becomes intractable. Suppose I rolled the dice 100 times. I can't enumerate all the possible outcomes that can happen in that case, but I can calculate it. So we need to be able to do those kind of calculations. We have to use a little bit of thinking to do that, and that's what we'll come on to. That's what our counting is about. So let's get past these examples and get to the counting. So the first sum rule of counting is a grand name for it. It's a really trivial thing. Suppose we have two sets of outcomes, and they have to be disjoint. So it has to be that all the outcomes in set A don't belong. There's none of them in set B, and vice versa. So it could be that we throw a dice once, a six-sided dice once, and that gives us our set A. We have 6 outcomes, and then we throw a 20-sided dice a second time, and that gives us the outcome of set B. Because there's 2 different dice, it's 2 different sets of outcomes. And then we suppose our experiment is we're going to draw an outcome from either of those. So we're either going to have thrown the 6-sided dice and we get a number from 1 to 6, or we've thrown the 20-sided dice and we get one of its numbers. How many possible outcomes could we get? Well, we could get 6 possible outcomes from the first dice, 20 from the second one, so there's 26 different possible outcomes. If we're tagging the number, so number 1 from the 6-sided, number 1 from the 20-sided, right? We'll call those 2 different outcomes. And so to get the number of possible outcomes, we just add them up, right? So that's the sum rule. It's very straightforward. So cleaner examples than my dice example. Suppose we have 2 sets of observers, one in Dublin, one in London, 100 in Dublin and 50 in London. A web request comes and we've got to pick a server to serve it. So we can either pick one of the servers in Dublin or one of the ones in London. There's 150 to choose from. That's our different possible outcomes. And then a second rule for helping with counting, also very straightforward, is the product rule of counting. And that's where we have pairs of experiments happening. Suppose we're going to do 2 experiments now. So we're going to say we've got a 6-sided dice and we're going to roll it twice. So experiment 1, so that's the first roll, can have 6 outcomes. And experiment 2, we're going to roll it twice. Roll it again, has 6 outcomes. And from the 2 experiments, there's actually 6 times 6 possible outcomes, 36 possible outcomes. And the way to see that is just to enumerate it. So you can see here that suppose the first dice rolls a 1, then the second dice could be a 1 through to 6, right? So the 6 possible outcomes given the first dice rolled will come up a 1. Then suppose it came up a 2, there's 6 possible outcomes and so on. And so we end up, we just multiply them up. So that's the product rule of counting when we have repeated experiments. And we can look at some examples. So suppose we have a byte which is 8 bits in it. Each bit can take a value 0 or 1. How many different values can a byte take? Okay, so the first bit can take 2 values. The second bit can take 2 values. The third bit can take 2 values and so on. So by our product rule, we've got 2 times 2 times 2 times, so that's 2 to the power 8, which is 256 possible values. Here's another example, we've already done it. 2 6-sided dice, numbers are 1 to 6. How many possible outcomes? The first one dice can take 6 possible values, the second one can take 6 possible values. So there's 6 times 6 equals 36 possible outcomes. All very straightforward. Here's another one, just to finish up. Suppose we've got a hash table. Here's a nice computing one. So hash tables are actually based on probability and need some nice properties. So there's usually an assumption that every bucket is equally likely given an input. That's one of the properties you want the hash itself to have. Suppose we've got a hash table with 100 buckets. We put 2 strings in one after another. The hashes of the 2 strings should be uncorrelated, right? They don't depend on each other. So how many possible ways are for the strings to be stored? Okay, each string can be stored to one of the 100 buckets. So the first string could go to 1 out of 100. The second string could go to 1 out of 100. So there's 100 times 100, which is 10,000 ways the 2 strings could be stored. Of course, we couldn't enumerate 10,000 ways very easily at all. So already our product rule is saving us a lot of work. Now, there's a more general version of that which we've already kind of been using actually, more than just with 2 sets. We can, if we've got multiple experiments, suppose we've got 10 experiments, If you've got n1 possible outcomes in the first experiment, n2 in the second one, you don't need to have the same number of outcomes in each experiment. You just multiply them all up. And we already did that when we were looking at the byte. So that's the general version of the product rule. Nice and straightforward. So we can do some interesting calculations. So if we have a look at passwords, for example, suppose we've got a password which is 4 letters, 4 lowercase letters, A to Z. So the A to Z, there's 26 letters. We've got 4 of them, so there's about 500,000 different combinations there. Now suppose we can pick from lowercase and uppercase. There's now 52 possible letters, and so we get about 7 million different possible choices of password. Now we add the numbers, we do that, we get up to about 15 million. So you see it's increasing pretty rapidly. Suppose we make the length 6, then it grows hugely, right? It's now 5 times 10 to the power 10. That's too big a number to be even writing out. Length 8 is going 10 to the 14. So you can see why you get people tend to be mandating mixtures of lowercase, uppercase, numbers and symbols and minimal password lengths, because the idea is that then you create many possible passwords and you get some security. So I'll point you towards this at the bottom here. I definitely recommend, if you have any interest in passwords, and we all do because we're all being asked about them, to enter them, to have a look at that paper, because it's really interesting. That's based on lots of measurements, because this is just nothing, not really anything to do with probabilities, but just about passwords. That this is assuming all these outcomes are equally likely. That's why we're interested in these kind of big numbers. But of course, people don't choose passwords like randomly, not unless you're using a password generator. That's why people promote password generators, because otherwise you'd do something like 1, 2, 3, 4, 5, 6, or password, or hello, or your name, or your address, or something like that. And so then these are misleading. The fact that there's a billion different possible passwords is actually misleading, because the possible of actual passwords people really use is much smaller. And you also need to be aware of the sorts of attackers that you're trying to defend against, whether they can brute force or not. Anyway, that's a digression. Just finish up with a generalization of the sum rule. So I was careful to say that the two sets of outcomes, A and B, for the sum rule are disjoint. So servers in Dublin or servers in London, and they don't overlap, therefore. You can actually generalize. We won't do too much of this, but it's worth being aware of. It's possible to have those sets overlap and still have, and the sum rule generalizes in a really obvious way. So suppose we've got an overlap between these two sets, A and B. So then we can count, to get the number of possible outcomes, we count all the possible outcomes of A plus all the possible outcomes in B. That's what this notation is, right? Set A, if the straight lines around it, it's the size of set A, number of elements in set A, number of elements in set B. Thing is, though, there's an overlap, right? So some of the elements, we've counted some outcomes in set B there, and we've counted them again because they're in set B, so we've counted them twice. So we've over-counted the number of possible outcomes. What we have to do is subtract one copy off. And that's what this guy does. So we take this as the intersection, this is the overlapping elements that are in both sets, and we subtract one of those copies off. And that's the idea. So it's given the grand name of the inclusion-exclusion principle. When there's no intersection through disjoint sets, this is 0, and we have the sound rule. The size of this intersection is 0, and we're back to our original sum rule. So that's worth bearing in mind. If you have overlapping sets, things still work. Just have to be careful to avoid double counting. We can do a quick example. Suppose we have, we're sending 8 bits across the network. Suppose you have to start with a 0, 1 and end with a 1 and a 0. So we're constraining it a bit. How many valid strings are there? So a few different ways we could calculate that, actually. Here's one way. So the set of possible strings that begin with 0, 1, well, we've knocked off the first 2 strings, so there's 6 remaining bits we could choose from, right? So there's 2 to the 6, which is 64 possible options once we've fixed the first 2 bits to be 0, 1. That's our set A. And then we've got set B, is that strings that end with 1 and 0, there's 64 of them too, because there's another 6 bits before that. And we're interested, the intersection between these two is the set of strings that begin with 0, 1 and end with 1, 0. And so there's 16 of those. We do a little bit of a calculation. And so the set of valid strings that start with 0, 1 or end with 1, 0 is the number that start with 0, 1, the number that start with 1, 0, and then we have to chop off the ones that start with 0, 1 and end with 1, 0, right? Because they're not possible. And then we end up with this number, 112.